If you're afraid of losing points on a test because of second-guessing cis and trans, this is the shortcut your exam brain needs. Hey there, ninjas. In this video, we're going to lock down exactly what cis and trans mean in organic chemistry. We'll talk about when you're allowed to use cis and trans, and just as importantly, when you're not allowed to use cis and trans. Cis and trans is about visualizing structures quickly, not precise naming rules. The big picture takeaway for this video is that cis and trans are relationship words. They describe the relationship between two groups positioned on a molecule, how those groups are oriented relative to each other across a ring or across a double bond. These are not official IUPAC names, and I'll show you later where that matters. Here's the only definition that you need. The words cis and trans are both derived from Latin. Cis means on this side, together, while trans means across. So the real question is, are two groups oriented on the same side together relative to each other, or are they on opposite sides oriented across from each other? Take a look at this cyclohexane ring with two methyl groups on wedges. Relative to the flat face of the cyclohexane ring, these two methyl groups are both oriented on the same side together, pointed towards you relative to the ring. They both could have been on dashes, but the relationship between these two methyl groups is cis. They are together on the same side of the cyclohexane ring. So these methyl groups are cis to each other. And informally, we would call this molecule cis-1,2-dimethyl-cyclohexane. Importantly, that's not the official IUPAC name for this molecule. The official version would need R or S labels for each of these methyl stereocenters. But the cis label allows us to visualize the molecule instantly in a way that R and S nomenclature really cannot. Here's a cyclohexane ring with two halogens. With respect to the face of the cyclohexane ring, one is pointed towards you, one is pointed away from you. Opposite faces of the ring. Therefore, this relationship is trans. So informally, we could say this molecule is trans 1-bromo-3-chlorocyclohexane. Notice something important. The two groups don't have to be adjacent to each other on the ring. Cis and trans work for any two groups oriented anywhere around the ring. So cis and trans define the relative position of two groups about the molecule. Are those two groups together pointing into the same hemisphere of the molecule, or are they opposite, pointing into opposite hemispheres of the molecule? The cis and trans label also works for alkenes, but only very specific alkenes. We can apply the cis and trans labels to disubstituted alkenes. On either side of the double bond, there's exactly one group attached to each carbon, two groups total. And when that's true, we ignore the hidden hydrogens and we ask ourselves the same question. Are these two groups together on the same hemisphere of the molecule, or are they across the pi bond on opposite sides of the molecule? We can address this by drawing a line parallel right through the alkene. Here, the methyl and the ethyl group are on opposite sides of the alkene. That makes this a trans alkene. This would be trans pent2-ene. When we draw the same parallel line through this alkene, the ethyl group and the methyl group are together in the same side of the alkene. That makes this a cis alkene. Cis pent2-ene. Again, these are shortcuts, not official IUPAC names. The official IUPAC name would require an E or a Z geometry label, and that's beyond the scope of this video, though I do have links to all of those videos in the description down below. For sure, cis and trans are faster for visualizing the molecule from the name than E or Z ever could be. Now here is where students get burned. If there are more than two substituents around the ring, we can't label the whole molecule as cis or trans. Cis to what? Trans to what? There's no single reference anymore. We can still describe the relative position of two of these groups. We can say the methyl and the fluorine are cis, the fluorine and the alcohol are trans, but for the whole molecule name, we would have to use R and S stereochemistry. And it's examples like this why R and S are the official IUPAC names and not cis or trans. Same warning for alkenes. If there's more than two non-hydrogen groups around the alkene, cis and trans is no longer valid because we lose that single reference. An alkene like this would have to be named with E and Z geometry, even though we still could talk about relationships as the isopropyl and ethyl are cis to each other and the T-butyl and ethyl are trans to each other. So why do we care at all? Why do we have two complementary systems, especially when one system is the official formal name and the other system is informal and breaks easily? It's because cis and trans are very easy to visualize, and that makes them very good for predicting the products of our reaction. Many reactions preferentially form cis products. Other reactions preferentially form trans alkenes. And that's true even if we don't care or don't know what the ultimate R or S or E or Z label will end up being. Saying something forms a cis product visualizes that product in our mind. Saying something forms an E alkene is accurate, but much harder to visualize immediately. So think about cis and trans as mental shortcuts, not official names. If you use them where they're allowed, organic chemistry becomes much faster. faster. If this helped, the next video you should watch is the one about E and Z labels for alkenes, because that's the system that replaces cis and trans when alkenes become more complicated. You've got this, ninjas.
I'm glad you're here with us for this training today. Check out these other videos in my playlists to see if there's anything else that can help you level up your ninja levels even further. As always, don't forget to like and subscribe.